2D dynamics, almost rocket science. So far, right, Chapter 6 talked about forces. We talked about the different forces you might have. We talked about an acceleration along one axis because of all of those forces. Chapter 7 said, hey, if you have more than one object, then you can have forces going in multiple directions, and you've got this interaction between things, and maybe there's a lot of other stuff going on. Well, to finish off that picture, to round everything out the rest of the way, we want to talk about what happens in the scenario that you've got maybe one object, maybe two objects, and the forces between all of them are not necessarily just isolated along one direction. Right? What happens when I've got maybe thrust on a rocket and it's a breezy day or something else like that? What happens then? Well, if we have a net force in the y direction and a net force in the x direction, we have an acceleration in both directions. Right? And that really doesn't change anything. Everything that we have seen so far, all of our old kinematic equations and everything else still completely apply. All of our old ideas about force still completely apply. Nothing has changed. This is simply, let's look beyond that condition that one of our directions is 0. Let's consider what happens when one of our directions, or rather both of our directions, are non-zero. So with that in mind, I'd like to immediately jump into one of these things, right? I don't think there's no new concepts here. That's kind of the fun part about this. We're just considering new ideas with the information that we've already got. So I want you to imagine, right? We do this a lot, our rocket-powered hockey puck. Let's imagine that it's got some sort of rocket strapped on top. It's got a thrust of 2 newtons, and the entire contraption altogether is a mass of 1 kilogram. It is released from rest on a frictionless table 4 meters from the edge, and the table is 2 meters tall. How far does the puck land from the base of the table? This is a classic projectile motion problem. The new condition, though, is that there is an acceleration in the x direction. Otherwise, nothing has fundamentally changed. So, I'm going to say let's take the next 5 minutes on this one. Right? You're going to need a lot of your kinematics. This is almost more of a kinematics problem than it is a force problem. So, think about this thing a little bit. Break it up into your 2 columns, x and y. Figure out what needs to go in each side. Think about those accelerations. And let's come back in around 5 minutes or so and see what you've got. All right, and for the theme of it and everything else, of course, the theme of the internet is that there is always some sort of XKCD comic for every scenario. And this is our one for friction and air resistance, vacuum, all of that good stuff. It's for everyone's benefit, I promise. I promise. We like to work in vacuum. We like to work without much friction. But friction's not the worst in the world. Really, it's just drag is the issue. Right? That's the big issue most of the time. So, let's actually take a look at this, though, and think about what happened. So, first things first. Of course, as always, we need to draw a good picture. Right? And when I say a good picture, it doesn't have to be good art. It just has to capture the details that we're looking for accurately. So we've got something like this, something like this, something like this. Man, what a drawing, right? When you think of modern art and everything else, the masters of art and what a table looks like, I think this probably ranks somewhere among them. So I'm going to call this, let's call it delta x1 and delta x2. Or, yeah, that's a, oh, not that. I keep clicking on the wrong thing. Delta x1, delta x2, between these two. Because what we've got at the very beginning, if I'm thinking about the things that they tell us, that the initial distance that it's going to cover in the x direction is 4 meters, that the height that it falls, so our delta y would be a negative 2 meters. We know that there is going to be some sort of thrust. So let me go ahead and color this thing in, and hopefully this doesn't just block out everything. Haha, all right. Feeling good about that one. Some sort of rocket. I have something like this, perhaps, and then there's, of course, fire, right? Something like that. So I think about all the forces acting on this thing right here. Now I'd say, okay, well, there is a normal force. There is going to be a thrust. And then there's going to be gravity pulling us down. And since there is no friction of any sort, and I can even write it out here, mu is equal to 0, say no friction or anything else like that, I know my y direction really doesn't matter, right? The y direction almost completely cancels out as long as I'm on the table. But let me draw a second free body diagram, because what happens once we launch off the table is a little bit of a different story. So here's kind of like my squiggle line. What I'm going to have is going to be the most careful drawing in the world. Let's see if we can grab this thing in its entirety. I'm even going to do something like this. Why do all of that extra work if we really don't need to? Area has no selected... What do you mean area has no selected pixels? Killing me. What is going on here? Selection mask. Paste it. I scream every single time. All right, well, never mind. We're just going to draw this thing from scratch. That's fine. Disappointing, but it's all right. So once we are flying off the edge, right, we're looking at a similar kind of scenario here. We've got still our rockets attached. That thing is still going off as much as it can. Our free body diagram now will look something like this. I've got mg pointing down. I've got thrust propelling me forward, but I have no normal force to keep me up anymore. So what that means is that we're going to now have some sort of net force in the x direction, some sort of net force in the y direction. But let me finish writing out some of these things that we know. We know the mass. We know the mass to be 1 kilogram. That works out very well for us. We know the thrust to be 2 newtons. We know the very initial velocity is supposed to be 0. It starts from rest, and then it starts flying off from that. And I think that's pretty much all the details that we've got. I think that's fine. So we need to find delta x2. So let me start with that. Let me say, okay, when I launch off the table in the first place, right? We started from rest, and then we ignited a rocket, and I have played enough video games to know that when you light some sort of rocket, it goes forward. So I have to imagine that when I launch off, there is going to be some sort of velocity there, and to the point that I might even say, let's grab this thing. And let's even move it a little bit so it's like right here. Right, so we're essentially off the edge at this point. Once we are off the edge, the normal force no longer is doing anything for us, but we have some sort of velocity as we launch off like this. So let me call this V1. What direction does V1 point in? Any guesses on that one? Yeah, to the right, horizontally, and that's a better answer because I haven't specified my axes yet, but now's a fantastic time to do that. So it's pointing in the positive x direction exclusively, right? Because it's been gliding along the table the entire time. There's no y velocity here. It has not gone up. It has not gone down. It's gone across the table the entire time so far. So V1 is pointing exclusively to the right. So if I think about what happens over on this end, right? When I'm thinking about what's going on with delta x2, I could say, okay, well, delta x2 would be equal to, well, our initial velocity in the x direction when we launch times the time that it took to fall. So let's do that. Let's say something like this. And at that spot over here, this also happened at some t2, some amount of time between those two. I'll label it like that. And then whatever x acceleration that we have. So I'm going to say 1/2 a of x t2 squared. Okay. Well, piece by piece here. Delta x2, that is exactly what I'm after. I'm going to highlight that in orange because it's very important. I don't yet know what T2 is, right? It's going to take some amount of time for this thing to hit the ground, whatever that might be. I also don't know my x acceleration, and if I really want to be careful with this thing, I don't know V1 either. So we don't know anything. Yikes. Well, that's not the biggest deal in the world, because we're going to find some other things in this one. But real quick, before I completely jump off of this, do either of my other kinematic equations make any real difference? Are either of these going to be useful for me? What do we think? So I'm going to leave them here, but I'm not going to work with these too much. I've got a little bit of insight that these are not going to be super useful for me. And the reason I don't think they're going to be super useful for me is largely because I don't know anything about the final velocity. I know it does not match my initial velocity. We distinctly have an acceleration in the x direction. So I know it's not the same. So all of our old conditions to say, well, there's no acceleration, so these two are useless, that is not true anymore. There is an x acceleration, so these two might be useful. But they're asking something about the final velocity in the x direction, and right now, I don't know that information. If it turns out we find it, then maybe I'll come back to this. But right now, let's kind of put these on the back burner. So with all of these things, we're after the thing in purple. That means we need to find the time, the acceleration, the velocity. Those are our big three. Let me kind of split up the responsibilities of these things. Where does V1 actually come from in our picture? What part of the problem is going to talk about V1? What's going to give us V1? What do we think? Yeah, I would argue the beginning part, right? Because the beginning part ends with V1. There's some, like, and that's our finale, that's our midpoint finale, is that we get to V1 from this thing gliding across the table. So let me kind of write these things out. So let me start with V1 comes from table. What about A of x? Where does A of x come from? From the forces. I would agree with that. And what about t? When do we know to stop the stopwatch, to say that's the end? What's our condition for that? When it hits the floor, exactly. And that's my hint, right? Because again, the x direction kind of on its own here would just say, you know, go as long as it wants to. The taller this thing would be, the more time it's got to fly, all of that good stuff. It would be perfectly happy to continue on, you know, off into the sunset as far as it could go. But T2 actually stops. We hit that final time when the puck runs into the ground, and that tells me my condition. So T from Y kinematics. Whoops, should probably put a space in there, right? That is the proper way to write out words. From Y kinematics. Okay, so with that in mind, and I'm going to move this over a little bit here. Let's move this thing over here so we've got some, a little reminder of what we're looking for in this. What's probably the easiest place to start? What do we think? Of these three, which one's going to be the easiest to find? I would agree. Forces, yeah, that sounds good to me. So I look at my forces and I would say, okay, well, I know that the acceleration in the x direction is going to be, and remember, we're looking at once we're off the table here, but this is true for the entire thing, actually. The acceleration in the x direction should be coming from whatever net force I have in the x direction. So let me say f of x, the net force in the x direction, is, well, I look at everything in the x direction, it's t, is equal to m times the acceleration in the x direction. Not 0. So acceleration is equal to t divided by m. And if you would like, if you turn this into a number right now, I would not be mad at all. I would not immediately replace it in the equation, but you are more than welcome to find that as a number for now. So, first one, done. What's the next easiest one to find? What do you think? Probably V1. I would agree with that. And in fact, what we're going to find here is that we did a good job with this. We have found this in a good order, I think, and this is why I like to do this in easiest first. Because let's go ahead and set the scenario up. We start with a velocity of 0. We are looking for a final velocity. That means that we want one of two equations, right? It just so happens that we want these two equations right here. Which one's going to be a little bit more useful for me, though? Right? Keep in mind that I'm pointing to these equations, but we're really dealing with delta x1. I would agree. The third works best. And why does the third work best? Because otherwise I would have to find time. My bottom equation right there says final velocity, initial velocity, acceleration, distance. I'm looking for final velocity. I've got the initial. I now have the acceleration that we just found, and I also have that distance. The other one, I would have to find time first, and that's doable, but it's more effort. So, of course, I'm going to take the easiest way possible. I'm going to say my final velocity, which is v1, squared is equal to my initial velocity squared, which is 0, nice and convenient, plus 2 times the acceleration of x times delta x1, because this is while we are still on the table here. So now I can say, all right, well, I know delta x, not delta x, I do know delta x. I know a of x is t over m. That means v1 is just going to be the square root 2t delta x1 divided by m. Same deal as before. If you want to turn this into a number right now, I am perfectly happy with that. That is totally fine by me. We don't have to carry this expression forward forever. It's not a big deal. But for two of these things now, we've got them. Now we are focused on what goes on with our y direction. So that's our last missing piece. So I don't really need to ask what we're doing for this one. But the question will come, which equation should I use? First kinematic, second kinematic, third kinematic. What are we thinking? I would agree first, but why? What do we not have? I don't know any, well, I don't know time. That is true, but I'm looking for time, right? Remember, kind of eyes on the prize here. We're using the y equations to find time. I don't know anything about the final velocity, though. I could find it, but I don't have it right now, and I would have to find it first to solve out for something else. And why bother with that when I have one equation that wraps up everything nicely for me? So let me do the same thing, but now for y. Let me say, all right, well, this is going to be delta y is equal, my initial velocity in the y direction. Delicious. We love that. Minus 1/2 gt squared. The rocket's not pointing up. It's not doing anything else like that. It's just pointing directly in the x direction. So the y velocity, or the y acceleration, I should say, has not changed at all. That's our classic negative g. There is a homework problem. There is a homework problem where there is some sort of rocket, some sort of thrust force that does have a y component. So keep that in mind. That might change in the future. It is not always just negative g. Sometimes we do have other forces in the y direction as well. But in this case, specifically, we don't. So, eye on the prize here. We are looking for T2. We have delta y. We know g. Solve out for delta t, or T2. So what I would say with this one is that I could say T2 is equal to the square root, and this is all right, negative 2 delta y divided by g. I'm scared. I see a negative inside of a radical. Am I going to end up with an imaginary time? No, because delta y is negative. It's all good. Time is not imaginary. It's one of our 4 dimensions of space-time. So, same deal. We can treat this as a number if we would like. Time is one of the big 4 dimensions that we have, so I'm not going to let anyone take time from me on that one. Time's a little bit wonkier than we typically expect it to be, but it is one of our 4 dimensions that we've got an all right understanding for. So specifically for these numbers, if you are kind of following along with that philosophy here, then what we should find is that our initial velocity when we launch off the desk is some invisible number. Give me a second. Oh no. Weird sounds, but the camera's not frozen. All right, fantastic. Normally when I start to hear sounds from my computer, that means everything's about to crash. 4 meters per second on that one, 2 meters per second squared from our acceleration. And our time should be something like 2.639 seconds. So we go back up to our initial equation. We say we've got all three of these at this point. I see 3 checkpoints. That means the only thing in my top equation with delta x that I don't have now is delta x2. Exactly what I've been looking for this entire time. Carry this thing down, plug in all of our numbers. I asked for that to be in black, please. Thank you very much. Plug in all of our numbers into this thing and just crunch right through. Delta x2 we find at the end of the day should be something like 2.964 meters. So this is my strategy for a lot of these things, right? Anytime I have a change of my forces, this is the same deal as when we were working with kinematics, right? Every single time we did something to change the acceleration, I said, draw a line there, split it up. What happens exactly at that point will link the beginning and the end, right? There's this kind of thing where reality does not allow discontinuity. If you remember discontinuity from pre-calc and calc 1, that is not a thing that we're allowed to have in physics. We can have like a sudden change in acceleration or anything else, but reality does not like discontinuity. So I know that this state links the two together. Even if my acceleration or my forces are going to change, that's totally fine. I just need to make sure to keep those things separate. Talk about why we're doing these things. Go through, describe all of them. Because again, like one of the things that I've got on this one, if you're looking at problem-solving strategies, when I'm writing these things out in solutions, I'm talking through my steps. But if I'm writing them out physically, I will actually put in the words for what I'm about to do and why I'm doing them. And there will never be a donation button on the Twitch page. Strictly demonetized. But that's kind of what I recommend for a lot of these things. Could I show Finding Time again? Absolutely. Let me go ahead and zoom out for all of those things. Like, this is my strategy that I want to talk through all of these steps. I want to essentially have an idea of what I'm going to do before I start writing down these equations. I'm talking about these things, even if I know that I'm going to be looking for some variables. I want to talk about why I brought an equation in the first place, and then I can pick it apart and figure out what I need to do from there. But I'm always writing down some words before I take my next step. I'm talking about what I'm about to do and why I'm about to do it. And that's a big thing. That's a really big thing. That's, you know, that is a practiced skill. So, here's a fun one. 5,000 kilogram interceptor rocket is launched at an angle of 44.7 degrees above the horizontal. The rocket motor gives a thrust of 140,700 newtons. Find an expression for the trajectory. This is not something that we have done in quite some time at this point, but we're essentially saying, okay, what we're trying to do here is we need to find some way that we can describe where it's going to be in y if only we had the x position. That's an important deal here, and that's a little bit tricky at first. It's not something that we've done so far. What you need to do, what is the link between x and y? What is constantly that link between the two? Time, exactly. You need to use time to relate those two position equations together into one expression that does not have time anywhere, that only depends on y, x, and those other variables that you need. No time in the final equation, though. So, once you've got that, of course, sketch the trajectory. Go ahead and visualize what that thing should look like. And then finally, we want to make sure that we are all on the same page with this, that we've got a good equation that works for it. So find the altitude above the surface, so that is your y position, when the rocket reaches the speed of sound, 330 meters per second. So I'm going to say the next 6 or 7 minutes on this one. It is a little bit more difficult, but let's take the next 6 or 7 minutes to work on this one. If you guys have some questions partway through, I am happy to answer everything. I am sitting right here or grabbing coffee, but otherwise I'm happy to answer questions as we have them. But give this a go. Think about this one a little bit. Give it a, you know, the classic college try. All right. I think it's probably a good time to start taking a look here. So, let's start, of course, with a nice pretty picture. somewhere right around here. Go ahead and draw some of these things out. And so let's go ahead and actually, we'll start with a rocket here, I think. So something like that, like that. I don't know what, something like that. It's got like a nose cone or something. It's got, rockets have fins, right? Oftentimes that helps guide them in one way or another. Some fire coming out of the back, of course. There's always like a red stripe or something for some reason, and then like they make the nose cone bright colored red so you can see it coming ahead of time, I assume. Something like that, right? So let's draw our axes on this thing, and I'm going to put this thing on some sort of graph picture here, right? And not just because my solutions have got it. Well, I made them in my solutions in the first place because I think it works a little bit better to really show, hey, this is an angle 44.7 degrees. And there's a reason that it's exactly at 44.7 degrees, but we'll talk about that in a second here. We know that if it's launching this way, then the thrust coming out of the back of the rocket comes something like this, right? It is not dedicated to one single direction. It is split between the two of them. But similarly, the entire rocket is also going to face some sort of gravitational force as well, right? So those are the two things to contend with, and we have picked our angle very carefully for all of this. We are given the mass, 5,000 kilograms. The thrust, 140,700 newtons. What else do we have? We've got the angle already written down. Well, we can go ahead and write this thing. Angle 44.7. And we also have finally that our initial velocity when we start is actually 0. So we need to find some sort of expression that ties together y and x, which is a little bit strange at first, but let's see what goes on with this. So what I'm going to say with this one is that to find some sort of trajectory equation, I need to have an idea of what x is doing, I need to have an idea of what y is doing, and then I need to see if I can take those two things and wrap them up together in some way or another. So let me go ahead and do that. Let me say, well, let's look at the x direction. In the x direction, should probably label these directions. In the x direction, I only have the thrust, right? The thrust is split up in x and y, but gravity is pointing in the y direction. So if I say f of x is equal to t cosine of theta is equal to the mass times the x acceleration. Perfect. Okay, so we've got that in our back pocket here. We can do the same thing for the y direction, except now it's going to say something like t sine of theta, that propels us upwards, minus mg. And that is equal to the mass times the y acceleration. So from both of these, I'm looking for something to do with trajectory. I would like to isolate out my acceleration first. And the entire reason that I'm doing this is so that I can get out of dynamics land and I can go back into kinematics land. So that's what we've got so far. Now we say dynamics are done. We're done with all of our forces. Now we're looking at our x and our y positions. My three kinematic equations, kind of in order as we've got them. I've got my delta x, I've got my v final, then I've got my v final squared. Which one of those three is probably going to be the best one to use here? As we're looking at these things, what are we thinking? Can even scroll back up to these if we'd like another look at them. Yeah, I would say position, time, initial velocity, right? Because right off the bat, we said, okay, well, we need some way to link together x and y. Our end goal, and we can even write this, we need to link x and y. Not Andy. Y. So we say, all right, well, the only thing that actually ties in between those two, the initial velocity or direction or whatever else, that all gets split up and then kind of divided into their own columns. But time actually kind of goes with both. So we say use time to relate those two together. So time is one of the variables I want. Then I also think about this. I know the initial velocity in each direction. We know V naught is equal to 0, so that's appealing, of course. And we also know the accelerations. So I would agree the top equation here is going to relate a lot of that stuff. I've got some sort of change of position is equal to the initial velocity, 0, plus acceleration times time. And of course, there's some more finer details than that, but let's do that. Let's say our x position at any point would be equal to, well, initial velocity, done, plus 1/2 a of x t squared. And I could say the same thing for y. I would say my y position, I start from ground, my initial velocity is 0, plus 1/2 a of y t squared. Now, we said we needed to relate these two together. I wanted to use t to combine these equations together into one, and in each equation, I see t squared. T squared is a shared variable. So, let's use it. Let me take my x equation. Let me say 2x divided by the acceleration in x is equal to t squared. Now I can take that over to the y equation. Y is equal to 1/2 acceleration of the y direction times, we plug in t squared, 2x over a of x. The 2's cancel out. Then I've got this acceleration thing. Y should be equal to a of y over a of x times x. A of y, a of x, those are two constant values that we had found earlier. Now, this thing can turn into a little bit of a nightmare if we're not careful with this. So what I would like to do is I would like to actually find numbers for these things. What we can say is that the a of x should be right around, and it's actually pretty fine here, 20.00, or just 20.0, this is I've got it, meters per second squared. The acceleration in the y direction is something like 9.99 meters per second squared. Is anybody really upset if I call this 10? And don't lie and say that you are upset by that. Nobody's upset by rounding something like that. 20 over 10, this is approximately 2x. Whoops, x over 2, what I should have said. A of y is the smaller one. A of y is only 10, a of x is 20. So our final trajectory looks something like y is equal to x over 2. Nice and easy. That means that our trajectory is just something like this. A straight line. Right, because we need that extra little bit of boost from the rocket to make sure that we are essentially not just falling back down, but then other than that, this is going to completely be fine, and it's kind of moving like that, right? Where it's got a little bit of an angle above its actual trajectory here, but otherwise it's moving in a straight line. How do we feel on this so far? I know we've only done parts A and B, but let me zoom out so you can actually see this work. How does it feel? Could be worse, I agree. We could, of course, make it worse. So let's dive into part C here. We're asked to find what happens when we reach the speed of sound. Let's do that. What is y when v is equal to 330? So keep in mind, what we're asking here is not for v of x, not for v of y. We're asking for the speed, essentially. That means that our velocity here, or our speed as we have it, 330 meters per second, those are terrible looking threes, that's disgusting, is equal to the square root of my velocity in the x direction squared plus the velocity in my y direction squared, right? That's a really important step here. It's not either of the directions we're looking at specifically, it is the total velocity vector combined. So then, we need to find what is my expression for v of x and v of y. What do we think? Do we have any good guesses here? What is my final velocity in the x direction? For any time, regardless of whether or not it's 330 or anything else like that. You know, how do I find that expression? Which expression is probably the best one to use? Second one, I would agree. Because let me take a step back for a minute. I probably didn't, rationalize this one enough here. We're asking for y when 330 meters per second is our speed. How do we know some sort of relationship between those two? Well, there's, technically speaking, a couple different ways that I can imagine this one. One of the ways that I could do this is I could try to find Vy. I could try to find Vy from this, and then I could move forward with that, but I run into a little bit of an issue of, it's doable, but it's really nasty, because I don't know, maybe I could use v of y, but then I'd have to find v of x first, and that's a little bit spicy. So instead, what I'm thinking here is let me figure out how long does it take to get up to 330 meters per second, and then plug that in. Find the time, plug it into the y equation. So, when we have something like that, I could say, all right, well, my x is simply, since we start at 0, a of x times t squared plus a of y times t squared. There's a t squared in each of those. Let me make my life a little bit easier. Let me pull that t squared out of the radical. So now this is t, whoops, not equals, times square root of a of x squared plus a of y squared. That is all equal to 330. That is time, when solved out like this, 330 divided by what we had just found on that one should be something like 14.76 seconds. Why is it incorrect to use a triangle with angle 44.7 degrees to solve for the x and y velocities? So the x and y, as we've got it, that 44.7 is not necessarily the path of our velocity, right? Keep that in mind. What we have just found with the trajectory is saying that basically, the angle that we're taking is not 44.7. That is just the angle that the thrust is at. But because gravity is also getting involved, that is not the angle of our velocity. We could do it that way, but we would have to find a different angle. And that angle specifically is something like 35? 26.6. Is that right? 26.6? That sounds reasonable. Yeah, so it's not the 44.7. That is just the angle of our thrust. So, 14.76 seconds. We look back to our y equations here. We say, hey, there is one very nice, clean y equation right here that we could use. I know my acceleration in the y direction. I now know my time. I can plug all of that stuff in. Y is equal to 1/2 a of y t squared, for a final answer of 1,088 meters into the sky. And there we have it. Don't do that. Don't. How did I find t? From this expression right here. I said that t, I took my, I broke up velocity. I said, okay, I know the hypotenuse of the velocity as this thing should be in some way or another. Let me go ahead and draw this out. If it's moving up like this, and I know this is not a great triangle, but I know the v is equal to 330. I've got my velocity in the y direction, I've got my velocity in the x direction. So that's what this expression is doing. That's saying 330 is equal to all of those things together. Then I said, okay, well, what are those velocities actually? This is my velocity at this point in time. For any of those things, I'm using the equation that v final is equal to v initial plus the acceleration times t. And we said, well, in both of these, both in x and y, the initial velocity is 0. I can just take my x acceleration, my y acceleration. It's the same time shared between the two of them. Square that thing up. Pull out t because I've got t squared plus t squared. And then divide over by this radical. Feel better? Go ahead and zoom out a little bit on this one so you can get a clear view of everything that's happening there. A of x squared and a of y squared, we had both of those. Those are numbers for us at this point, right? A of y squared would be just 10 squared. A of x squared is just 20 squared. So my intermediate step between those two, move this down a little bit. My intermediate step between these two would be something like, dragged a little bit too much there. T is equal to 330 divided by, so what is that? 20 squared plus 10 squared. You like drag? We are going to find an expression for the acceleration in x and y given some two-dimensional drag. So, you know the expression for drag, right? It points against our velocity. We know it's going to have this strange velocity squared thing, but the issue is that if we throw this thing up at some strange angle, then it's going to be the same magnitude no matter what. That magnitude just depends on the speed, but the direction that it goes might be split up. So what I want you to do is assume this thing has already launched. It has some speed v. It is currently moving through the air, but drag is something that we actually have to worry about. Just use rho and c. This is a completely symbolic problem. Use these things together to try and find an expression for the acceleration in each direction. I'm going to give you guys just about 4 or 5 minutes to take a look at this one, and then we'll take a look at it together. Sort of nonsense do we have going on in chat right now? How's about we take a look at this thing together? Coffee's actually in hand. I didn't realize that I was completely out of the pot that I had, so I had to improvise very quickly. For anyone keeping track of my coffee habits. So, let's go ahead and take a look and see what we got here. This is a little bit of a strange one. And the answer is going to look a little bit weird at first. But we've got something, imagine we've got something like this. And let's say that it's starting with, we'll even match some of the colors here. Let's do a velocity that looks like this. Dotted line to say, hey, remember, not force. That means drag goes against it, like this, at some angle. So I don't know what that angle is necessarily, which is a little bit strange at first. Let's take a look at this thing again to say, okay, find expressions for a of x and a of y for a mass that includes the aerodynamic drag model. Okay, so let's say that we do know something about the actual velocity vector. But there's a couple different ways that we might consider writing out this expression. I know I have given you kind of just a bunch of random things to work with and see what we got on this one. I'll talk about a couple different ways that we can consider writing this. But for now, what I'm going to say is that we have this angle theta relative to x. And that means that similarly, my drag should have this angle theta relative to x. just on the other end of this thing. So then, as I have this thing, let's, you know, as we would have this thing as well, we have also to contend with, I probably should have mentioned, we certainly do have this. If you don't have this in your model, that's all right, but we should also have gravity. Because we're tossing something through the air, right? We're, I don't know, touching a beach ball or something else like that. So, here's what we've got, right? We need to think about what goes on in each direction with our forces first. So if I think about my x direction, for example, I would say that my x direction is going to be equal to, well, the negative drag times cosine of theta. That's all fine. Happy with that for now. The forces in my y, I would similarly have drag, d sine of theta, but now I also have gravity pulling me down. Okay. So, between these two, if we are to find our acceleration, this is not anything crazy at this point, right? Because we can kind of see our expression. We just need to plug some things in with this. This is not the end of the world, necessarily. We would just say, all right, well, my acceleration in the x direction, I take this term divided by m. To make it complete, I would like to actually plug in what is drag. Well, that's going to be negative 1/2 c rho a v squared divided by m times cosine of theta. Okay, one way to do that, a of y can be written out similarly. Now it's going to be a little bit more messy, but this is going to be a negative d sine of theta divided by m minus g. This would then become negative 1/2 c rho a v squared divided by m minus, times sine of theta minus g. Yikes. So now if we really needed to be careful with this thing, and I would argue we might need to be careful with this thing, then what we actually will end up having is, let's imagine for a second. We have this vector. Let's say that we know the vector, but we don't necessarily know theta. This is how they write this out in the book. What we would need to do is we would need to say that v of x and v of y, this is equal to v cosine of theta. V of y is equal to v sine of theta. That would mean that we would have to recreate these expressions. I've essentially got v squared times cosine of theta. Let me go ahead and write this out on the side here. V squared cosine of theta is equal to v times v of x. V squared sine of theta is equal to v times v of y. In both of these cases, v is equal to the square root vx squared plus vy squared times v of x. And so I'm writing all of this out because this is a different way that you can consider notating all of these things. Right? The angle is the easier way to write them out, I think. I think dealing with sine and cosine is an easier way to do this, but that is not always what we would have in a problem like this. And for the most part, we're not doing these problems for a reason. Right? So I could finish by plugging all of this stuff in. These are fine expressions, I think. But if you'd like to crank it up a notch, then what we could do as well is we could say that this is negative 1/2 c rho a. Now this is square root of vx squared plus vy squared times v of x divided by m. And we're going to have something similar for a of y. So the question comes up, is using drag in problems fun? No, it is not. Don't you lie to me like that. Don't you be lying. Don't say it's as fun as using friction, because friction is very bearable. Friction is very easy to use compared to drag. So yeah, if you ever wonder, why don't we consider air resistance? This is why. Of course, there are many problems that have to contend with this, right? And when I say problems, I'm not just talking about problems from a textbook. I'm talking about problems in reality, right? If I want to throw a balloon, drag is a really, really big factor. If I'm looking at a falling feather, you know, there's all sorts of different applications where you do have to consider air resistance. But a lot of the time, once we get into situations like that, by the time we're being that careful, we're using much more accurate drag equations than this, and we are also using computers to model that for us, right? There are not like closed form solutions in the same way that are just as easy to deal with here. You know, once you have a complex enough system, we are using computers to model those systems. So I'm not overly concerned about these things. I would like to show you why, to really give you a little bit of context as to why don't we think about air resistance that much, because it's very difficult, and we will try to focus in on problems where it's not a big deal. There's a reason that we're talking about things like hockey pucks and cannonballs rather than beach balls and feathers, because for the hockey pucks and the cannonballs, drag is not that big of a deal. We're designing these problems with that in mind. So, I think we've seen enough of this, right? Would you agree? I would say let's go ahead and look at our last problem for the day. Something's going on outside. Don't know what it is, but all right. This one's just a little bit different. What we've got now is, let's say there's no real appreciable amount of drag, but there is a very strong breeze. So let's launch some sort of projectile. We launch it at a speed v0 with a headwind. That means the wind, you launch the thing forward, the wind is blowing back towards you. So the x direction force would be this negative force from the wind. Find an expression for the range, that is the delta x when it lands, and find an expression for the angle for the maximum range. I'm going to give you guys a few minutes to work on this one. And then we will take a look at this together. Let's say the next 5 or 6 minutes. All right. Ready to start taking a look here? So what I have to imagine in this case is we're going to have a little bit of a different trajectory than we're used to. And we actually don't have a lot of given variables, and that's by design, and that's okay. That's not going to stop us from doing anything here. But let me get a sense kind of if anybody has ever seen any sort of realistic trajectories. This is a little bit of an interesting thing, because what happens now is that we don't follow a parabola shape. We've got a parabola mostly, but then it's going to have this weird thing going on. So if we launch from somewhere, got our cannon, we launch off like this at some initial velocity, our trajectory is going to end up looking something like this, where it's like a collapsing parabola almost. It's like leaning in some way or another. So this is what we've got to contend with this to go around. And so let's think about our free body diagram. We would have regular projectile motion as typical. I'm not going to try and draw on this picture. Let's draw off to the side here. Let's label Y and let's label X. Our object, as we would have it, of course, has this initial velocity pointing like this. V0. The vectors acting on it from here. We have this headwind, F of W, and we have gravity pulling us downwards. These two things together are going to be causing some sort of acceleration in not only the Y direction, but also in the X direction. So we're asked to find the range. That is, which variable? Range is a fancy way of saying what? Delta X, exactly. So the only things that we're actually given here is V0, and let's say theta. Let's say theta for this thing. We know what theta is. It's a variable that we'll use. We also know that this headwind is the thing. But that's just about all that we've got right now. And maybe the mass. Let me think here. What else do we have? Suppose projectile mass m, speed v naught, yada, 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 yada. Find a expression for the range. So we're going to treat theta as if we know it, and then in the next part of this thing, we'll actually find something for theta as well. So maybe it's v squared sine 2x over g. Not quite. That was true when we were dealing with only gravity, but with this headwind, everything's a little bit messed up. So first, we're going to be tasked with finding delta x. Go ahead and label it on our picture here. So let me start there. Right, let's just take this thing all the way from the end and let's work backwards from that. So we say, okay, delta x, of course, which equation do I want to use in my kinematics? Do I want to use the first one or the last one? What do we think? Do I want to think about time or do I want to think about the final velocity? I've run into a little bit of an issue here of I don't necessarily know what my final velocity is. Let me show this. Let me write out both of these. We know in either case we're looking for delta x, but in the first case we would say we're going to take our initial v of x plus t plus 1/2 a of x t squared. Fine. The other option is that we take, say, v final x squared is equal to vx squared plus 2a of x delta x. So maybe we can leave both of these in place for now. But in either case, we are after delta x. We need time in that scenario. We need acceleration, and we would also need our initial velocity. But we can find the initial velocity, right? That's, I think, pretty easy, given all of this other stuff that we've got. We know the initial magnitude. We know the initial angle. We can find v of x from that. Same deal down here. We would need this, but the last thing that I'm going to highlight is this in blue, this very final velocity. So yeah, this is a little bit of an interesting one because in either scenario, let's go ahead and start with this. Let's kind of create our checklist of things. Let's go ahead and start with v of x because v of x I think is the easiest one to find here. We would say that v of x, simply put, is just the cosine times our initial velocity. Perfect. Done. Green check mark. Okay, a of x. Let's start with that one because both of those share that. We need that regardless. Where are we going to find a of x? We're not going to find that from y. We're going to find that from our forces indeed. Anytime we're talking about acceleration, there's a real good chance it's going to come from our forces. Because again, as we're looking at this, the x acceleration and the y acceleration do not interact at all. There is no real dependency between those two. So if I need to find the x acceleration, I can't find it from y. I need to find it from forces. In this case, I've got only one force going in the x direction. So that is to say, f of x is equal to negative force from the wind, should be equal to mass times the x acceleration. That is, my x acceleration is negative wind force divided by m. Check. Now the question is, do we try to find time or do we try to find final velocity? If we tried to find final velocity in the x direction, what would we do? What equation would we have to use for that? What do we think? What's the only other equation that uses final velocity? It would have to be our second kinematic equation. Exactly. So let me move this thing down a little bit so we've got some space, right? Because that is technically our third kinematic equation as we have these things ordered. But my last equation that I could write in here is that VF is equal, VFX, I should say, is equal to v of x plus a of x times t. If I wasn't on stream, I would have some words to say about that, some curses, a variety of them. I've got to find t anyways. I've got to find t anyway, so if I've got to find t, I might as well just use one equation to go through it. I'm not going to bother using two separate equations to do the exact same thing I could have done with one. So that's why I'm going to say for these two, it's not that we can't. It's that is extra effort. I would need to find an extra variable just to find, the thing that I'm looking for at the end of the day anyways. So if you decided to go with those two equations, you could absolutely still solve the problem, but it's going to be an extra step, and I'm going to try and avoid those extra steps when I can. If we're looking for t, I'm going to make the argument again that we say, we click the stopwatch when it hits the ground. When it hits the ground is something to do with the y direction. So what we could say is, there's a variety of ways that we could do this. I'm not going to write that equation out to start. We're looking for time from the y direction, knowing our final y position, our initial y position, our initial y velocity. I think I've said enough. The first kinematic equation has all of those things tied together. Final and initial position, 0, no difference between those two. Initial y velocity, go ahead and write it out up here. Same deal though, it's just a component of our initial velocity. Times t, that's exactly what we're after. Now this is going to be minus if I see, hey, gravity is the only thing acting in the y direction, and I can go ahead and just confirm that for sure. It's equal to negative g is equal to ma of y. That is to say our acceleration in the y direction is just our classic negative g. So I'm going to write minus 1/2 gt squared. I know v of y. I don't know t. I'd really like to know t. Take it a step down. Divide both sides by t. Solve out for t. Bam. Now we have an expression for t. We can come back up to our delta x equation, and this is about to get a little bit nasty. What I might do while we're here is I might just go ahead and say, let's plug in, this is 2 v0 sine of theta divided by g. That might be easier. We'll see. We're going to see. Now we're going to plug this all into our x direction. So let me clear up some space here. We don't need this stuff here anymore. We've already decided it's not very useful for us. So take t, plug it into here. And while we're here, let me give it a red check mark. Ah, we have this. Take all of the pieces. In black, please. Thank you. Oh, this is where it's going to get a little bit nasty. So delta x is equal to v of x times this. Plus, here's where it gets bad. Let's go ahead and plug in for my f of w as well while we're talking about it. So this is f of w over m times 2 v0 sine of theta squared. Well, all of this whole thing is going to be squared. Yikes. That's all right, though. That's not a big deal, because what we can do is we can say, well, part of this with my v of x, right? I can say the v of x is actually v0 cosine of theta, and then that part is where it's going to show up like our classic range, right? And let me write in this step real fast. What we're saying here is that 2 sine of theta cosine of theta is equal to sine of 2 theta, right? We had that old trig identity. Pull that out of our back pocket here. What we end up with is v0 squared sine of 2 theta divided by g minus the 2's are going to cancel out. The f of w, oh, there is an extra 2 hanging around though. Sine squared of theta divided by mg squared. Yikes. That's not so kind. And I'm going to tell you right now, that's not going to simplify too much more than that right now. That's I'm happy to leave that expression right there. I'm happy to leave that expression right there. So that is my range when we have a headwind blowing against us. This is not even considered drag, right? This is just considered, we've got a windy day, not considering air resistance. So, how do we find the maximum range? What do you think? Let's try this for a second. If we were to plot this out, say we can pick any theta. If we were to pick any theta, I'm running out of room here. I have managed to back myself into a corner apparently. But let's say not 45. Certainly not 45 anymore. Drag is messing that up. So let's say that we are saying pick a theta, find delta x. We can change this as we so choose, right? We can change any theta that we could want to plug in. That will give us some sort of delta x, right? Why am I doing this in the first place? Because I'm imagining here that as I do this, this is some sort of function. If we decided to put delta x on this axis and theta on this axis, if we actually plugged this into some sort of calculator, what we would find is some sort of nasty looking function that looks a little bit something like this. Kind of like our trajectory, actually. But I'm going to get some sort of expression that looks like this. How do I find the max point on this thing? Where do I say delta x is the max, as much as it possibly could be? What do I have to do for that? When the derivative is 0. That is exactly correct. Max, this is when dx d theta is equal to 0. Clapping indeed. Right, this is where we get funky with it. So now what I'm going to do is I'm going to say, okay, let me take this x expression. As I have it, let me take a derivative of this, and let's see what happens. I'm going to say the derivative of x with respect to theta. V is a constant, g is a constant. The derivative of sine of 2 theta specifically, should be 2 times cosine of 2 theta. And now it's going to get a little bit nastier. And then what I'm going to have here is, let's first pull away these constants. Now I'm going to take the derivative of sine squared of theta. So this is going to become, I'd have to do a chain rule. 2 times sine of theta times cosine of theta. That's my derivative as it comes out like that. Right? Let me take that same identity as before. Let me combine some things. So this is going to become 2 v naught squared over g cosine of 2 theta minus 4 wind force mg squared. And then we're going to have, this is going to turn into sine of 2 theta. I'm trying to find when this thing is all equal to 0. So I plug that in, and then I ask, what is theta going to be because of that? Let me write it out like this, and I know I'm up against time right now, so I'm trying to wrap this up as quick as I can here. But I love this problem. It's such a cool problem. So I've moved that over to the other side, and what I'm going to say is cancel out a 2. This is going to become a 2. I'm going to cancel out a g. That's going to go like that. And then I'm going to divide by cosine. And actually, I should have... I have forgotten a v squared. That should have been in there as well. V naught squared. V naught squared should have been in all of these steps, and it should have canceled out right here. So I'm going to say 1 is equal to 2 f of w over mg tangent of 2 theta. That is, tangent of 2 theta is equal to mg over 2 times f of w. The angle that we are looking for is 1/2 arctangent of this mess right here. And that is our maximum range. So, 1 minute over, which I apologize for, but that's what this problem looks like. Some sort of real mess in this one. And I don't think I've missed anything else in any of that. Oh, I'm off by an extra 2. I've got an extra factor 2 floating around in there. If somebody can find it, that would be fantastic. Will we ever have anything that intense on an exam? Probably not. Probably not. But maybe. Got to keep you guys on your toes a little bit here. Are there extra slides? There are. I'm not super concerned about them. Realistically, it's just mostly rehashing some of these things from before. We've seen these things already, right? These are all things that we have seen, but it's essentially saying, hey, we've got the same kind of deal with all of these things. We're talking about circular motion again, right? That is two-dimensional motion in the same way. So I wanted to bring this one up, but really we're going to hit this a little bit harder next time around. (8-1), yeah, something like that.